All right, welcome to the first session of the meeting. It's on time series clustering and classification. So I'll introduce the first speaker now, keynote speaker for this session. Professor Eamonn Keogh is Professor of Computer Science and Engineering at UC Riverside. He completed his doctoral work in 2001 at UC Irvine and has won numerous career awards in intervening time and a number of NSF grants, one of which has funded a series of tutorials on topics of machine learning classification, which are available, or information about which is available on his website. Well worth looking at. He's an expert in solving similarity and indexing issues in time series data, and he will talk today, welcome, on the topic of scaling time series data mining, scaling upward, I presume, to trillion data series. Okay. So, first of all, let me thank the organizers for inviting me here. It's a pleasure to be in their company. If Google can handle my accent, I'd be really, really impressed. I'll do my best to speak slowly. So let me jump right into it. And here's the outline of the talk. And I'm going to begin by arguing the following. And I use the word argue advisedly because I'm going to make claims here which actually contradict other people's research and papers. But I'm going to convince you that I'm right and they're wrong. And so my first claim actually is that similarity search is the fundamental operation for almost all stream and time search problems. If you can do similarity search very well, everything else turns out, I think, is easy. Classification, clustering, anomaly detection, and so on and so forth. That's my first claim. And I'll explain what similarity search is in some detail first. My second claim is also kind of controversial, which is that the similarity search problem actually is now essentially solved. We are effective and as efficient as it basically ever need to be, or ever can be in some sense. And now we should actually spend time looking at these higher level problems and at the fundamental search problem. Let me jump right into it with a 5-minute tutorial about what similarity search actually is, and then we'll move on. So similarity search requires us to understand what do you mean by similar. And that really comes down to what are the required invariances for your problem. I'll explain in a moment. And why is it so important to be fast? You probably already guessed why you need to be fast, of course, but I'll do that also. So here's a quick tutorial. It looks contrived, but it's a real problem we're working on. We have these large archives of historical manuscripts from about 800 years. And let's say we have a query. I find some interesting fish here, and I want to know, are there similar fish in 17th century Portuguese documents, for example? So I have my database. I want to search. Here it is here. And similarity search simply says, take the query, compare it to every single thing in my database, find the nearest fish, in this case probably that guy there, I'm guessing, and return it as the nearest neighbor. And that's all similarity search is. Now I said similar, and what do I mean by similar? Well, I'm going to have a distance function, here it is here, and distance function is simply a black box, and into the black box you put in two objects, two DNA strings, two fingerprints, in this case two fish, and it pops out a number. The number itself has no meaning, but the relative numbers do. So maybe the similar fish actually is 2.7 units, but a different random fish might be a much larger set of units here. And the question actually is, for any kind of data you have, time series in this case I'm mostly interested in, is what's the right black box? What property should it have? And these are the invariances. So for example, I want my black box probably in this case to be invariant to color. And why is that? Well, the early documents were scanned by Google. They were scanned in black and white. They were being cheap. So actually, I want the distance to be invariant to whether it's colorful or black and white. And likewise, the documents are scanned, actually they're not scanned, they're photographed from the distance, and the camera can move in and out, it can zoom. And so the size of the fish is actually only the apparent size. There's no information. I want to be invariant to this. And for many contexts, of course, the direction the fish is facing, left to right, right to left, makes no difference. I want to be invariant to this. So for any similarity problem you have, the question is simply, what do I need to be invariant to? And once you're invariant to those, you're in business. I should point out, of course, this is all context dependent. This is true for historical manuscripts, But in the real world, let's say underwater with a camera, color will make a big difference. And in the real world, a big fish might be a different species to a smaller version of it. And even this left to right asymmetry actually may not exist in the real world. There are some fish which are asymmetric, flounder in place, and they're asymmetric to the left and to the right, and this actually would make a big difference. So understanding the invariances are very important, and we'll get to those for time series shortly. And then finally, why is speed so important? Why do we care? Well, the obvious reason is, of course, first of all, that the size of the data set might be quite large. We might have 1 million or 1 billion or more objects in this, and measuring distance function at every one could be quite slow. But actually, more importantly for what I'm going to talk about today is that very cool algorithms actually call this function as a subroutine many times, maybe 1 million or 1 billion times. So no matter how fast one iteration of this is, doing it 1 billion times could be slow, it needs to be fast. Okay, one last little point here, which is useful a little later, is if I want to actually, I could search for those fish in the kind of time series space. I can actually take a shape, I can find the center of mass, I can unwind it into a one-dimensional sequence, and I can consider a one-dimensional sequence. It's actually the lossy transform. And actually, I'm sure there's two reasons, one which is we'll pop into a few slides later on, and secondly, it shows an important point, which actually is for many of these problems, the interesting part actually is changing the data from one data source to another. So I'll show you an example of this later on with DNA to time series, but you can change data from one form to another form all the time. And as it happens, it's a useful trick because often problems are easy to solve in one format. Lovely. We're finally ready to look at streaming data, we can talk about streaming time series. So I'm going to spend the next half an hour talking about the utility of semantic search. Again, because my claim is, if you can do this well, almost all problems are very trivial to solve. So here's a real time series, and semantic search simply means that I could grab a template, let's say this section here, and I could ask, where is its nearest neighbor, its most similar object, anywhere else in this time series? And my guess actually is it would match pretty well over here, for example. So with that one core subroutine, let's solve some problems. The first thing I want to do actually was hint at in the introduction, is find an outliers, anomaly, novelty, and so forth. How do we do this? And there are hundreds, maybe thousands of papers trying to do this. But here's a nice way to do it in semantic search. Let's imagine take a subsequence here, and we ask, what is its nearest neighbor? So this guy here, it's probably nearest neighbor is probably this guy here or this guy here. And actually, for every single subsequence here, I could ask the question, what is the nearest neighbor? And the one that has the largest distance to its nearest neighbor, I'm going to call it a time series discord. As it happens, this one section here in red has a very large distance to its nearest neighbor anywhere else, and hence it's called the discord. And I'm going to say I think it's an anomaly. And of course, as you can guess in this annotation here, it actually is truly an anomaly. It needs to be detected and flagged and whatnot. So this is the way I introduced about 7 years ago to find anomalies in time series. And reviewers initially didn't like it. They said it's just too simple. But later on, empirical evidence showed actually it seemed to work very, 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 very well. And people said, well, it works in spite of being so simple. But actually, that's not true, of course, right? It works very well because it's simple. Because you don't have 15 parameters to tweak, and you can't impose your ideas upon the data set, and it tells you what's anomalous, you don't tell it in some sense. So fairly recently, within Kumar did a kind of a bake-off on 19 data sets with 9 different techniques, including this one. And as trivial as simple as it is, it works beautifully. It wins basically every single time. So my point is, again, that the simple idea of semantic search lets you solve a problem that people find quite complex, finding outliers. Let's look at another example of when we do semantic search. Let's do clustering. So the first thing is, here's a trick. You can take DNA, which of course we know is a string of ATCGs, and we can make it into a time series. And it's actually a neat thing to do. So here's a DNA string for a human. And if we see a G, we're going to take a step up 1. If we see an A, we're going to take a step up 2. A C, take a step down 1, and so forth. So if I scan across a DNA string, I can make a time series. Here's a picture of it. It's actually kind of an interesting picture because it actually has its property to be kind of spectral and everything else. But the point is, we have a time series. And you may know that for most mammals, this string is about 3 billion base pairs long. It's quite a long string. Okay, so I've randomly taken a chunk of human DNA, about 72,000 base pairs, 72,000 time series data points long. Here it is here. And I'm going to ask the question, can I find its nearest neighbor for 5 other primates, and then cluster those nearest neighbors? So So I've done that. Here's our human DNA here. And the nearest neighbor, perhaps not unsurprisingly, is from chimpanzee. And the next nearest neighbor is from a gorilla, and then from an orangutan, and so forth. And as it happens, this clustering is actually the correct clustering for the tree of life from external evidence. And the branch lengths even are almost like, they're not perfect, but pretty good. So just in passing, this actually could be a problem with scalability, right? Because not only do you have 3 billion base pairs for each primate, but you also have to go left to right and right to left because the DNA can be transposed. So there's literally a few tens of billions of base pairs. Making it scalable is interesting. I'll talk about that a little bit later. The point is, it's a cool cluster you can do with semantic search. Here's a neat classification problem you could solve. So here's a mosquito, and which mosquito is it? There are 3,528 different species of mosquitoes. Which one is this female here? And actually, we can solve this with semantic search too. Now, I could solve it, ironically enough, with DNA, but DNA actually is still quite expensive and slow and clumsy. I want to do it on the cheap. And I'm going to do it with time series once again. So I'm going to take the insect, and I put it into an insectary, and then I put it with sensor in the insectary just to watch her 24 hours a day. And I watched her for 24 hours and watched how active she was. And so this is from midnight to midnight, one day. And during the nighttime, there's a little bit of background activity. But an hour before dawn, she senses dawn, and she's very, very active. But the moment the sun peeks over the horizon, she simply stops. Does nothing basically all day. And then again, the moment the sun sets in the horizon, the huge burst of activity for 1 hour, and then she begins to do some background again. So I've had this pattern. You might call it a circadian rhythm. It's actually a deal rhythm, but it's basically the same thing. And my claim actually is this is all I need, because as it happens, I've been collecting these deal rhythms, making them basically, from many, many, many insects. I have a nice archive of them, and I can measure the difference between the one I've observed for that female insect with all the ones I currently have, and look for the nearest neighbor. And the nearest neighbor here is a pretty good fit. It's actually some Culex. And that's my prediction for a species, which actually happens to be correct. So the pink one's average over many, many females, a little bit smoother, but it's basically the same shape. No kittens in daytime, and these spikes before and after dawn. So this actually is a little bit offline, it's batch, but just like I've mentioned in passing, I want to actually do something like this, but in real time. So in particular, here's my ambition. Imagine an insect 100 meters away. I want to be able to detect that insect's sex and species in real time. That's a very, 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 very challenging problem. We've already made some progress with this. So in particular, if you're interested in really cool machine learning problems, I have some students who are, come talk to me. I got lots of data, I got lots of cool problems and sub-problems and sub-sub-problems on this very ambitious idea of classifying insects in real time from 100 meters away. But I'll do that offline. Let me show you yet another set of problems we can solve with semantic search, this time motifs. So this insect here, a bee leafhopper, is one of maybe 4,000 or 5,000 species of leafhoppers. These are the insects which cause huge problems to Murphy. And we're talking about maybe $10 to $12 billion of damage to plants every year. What the insect actually does is she drives her stylus, or actually could be a bee in this case too, I suppose, into the plant, sucks out the sap, and takes the sugar out of the sap. And the behavior itself is pretty innocuous, doesn't really hurt the plant. But if one plant has a disease, and this insect jumps from plant to plant to plant, the disease will spread to all the plants. And again, I'm talking about $10 to $12 billion of damage just in North America alone for these insects. And some cause problems for grapes only, some cause problems for almonds only, and so forth. This particular one actually, you might guess, the beets mostly, but it's other plants too. So it's a tiny insect, it's hard to study. How can we study it? Well, of course, we're mostly engineers and scientists here. Let's actually wire it up. So you can attach a small, tiny gold wire to the insect. It doesn't notice, doesn't care. And you can ground the wire to the plant or to the ground itself. And you can measure various things like resistance or whatever it is, voltage on this insect. And now the insect does its little business on the plant, and we get time series. And of course, we all love time series in this room. We can deal with time series potentially. But the problem is, when you do this for hundreds of insects over months or years, you get just terabytes and terabytes of this stuff here. And what do you do with that? How do you make sense of all this noisy data, right? It's very, very intimidating, of course. And up to a few years ago, at least, most people were doing this by eye. It was simply having my grad students go through this day after day, looking for interesting stuff. And my claim actually is that this is better than that. We can find motifs. So what are motifs? Time-space motifs are patterns which are approximately repeated in the data. So in particular, here's a zoom in. This pattern here, the red one occurred here. You can't see it in the scale, but trust me, it's there. And the blue one occurred right here. And so the pattern repeats itself almost exactly twice. And you don't believe that's a coincidence. Like something happened there causally, some behavior to make this pattern appear twice. As it happens, actually, this is a known motif. What it corresponds to is the insect taking its stylet, driving it into the plant, and then withdrawing it just to find a sweet spot. And this is in a very prototypical way, and this is exactly what you get. So we ran our algorithm in this data set, we found a known behavior, which is nice, but not that exciting. But of course, we can look for other motifs and find unknown behaviors. Here's exactly what we found. So here's a motif you can see it repeated twice in the data. Actually repeats itself quite a lot. These are two examples. And we actually have video with timestamps of this data. We can go in and look and see if it's actually happening. And this is actually an unknown behavior we discovered. So this is actually a different leaf hopper, same kind of thing. When it takes the sugar out of the liquid, it has some basically liquid it's actually now eject. This is called honeydew. It's also called manna from heaven. In the Bible, it's actually almost what manna actually is. But I digress. And when the bead goes large enough, she or he shakes its rear end to get rid of this little bead, and the bead bridges the plant, and it causes exactly this pattern here. And again, this is an unknown behavior. So here's a cool example of how motifs can find interesting behaviors. The actionability of this actually I won't talk about too much, but it has a bit of actionability. If we understand the behaviors, when we introduce controls like pesticides, like other kinds of things, maybe predators, we can now think about how the intervention changed the behavior. I'm going to change the behavior in good ways, not bad ways, of course. So one exciting thing we can do with motifs, I'll show you in a moment, is we can find rules in time series. This is actually very new work, unpublished actually, and I think very, very exciting. I mentioned in passing that the problem was apparently solved before, but it wasn't. It was later shown actually the algorithm that was shown before finds high confidence rules in quantum mechanical random walk data. So it finds rules, but it's definitely no rules. And the opposite is true. It cannot find a rule, but the most likely to find after one heartbeat is another heartbeat. That's a very obvious rule that we would see very quickly, clearly, right? But the algorithm can't find it. So my point is, this actually is not a solved problem, but I'm going to show you actually we have solved it. So here's a data set of time series, and the question is, are there any behaviors or rules in this we can actually find? And it's hard to say in this scale, but actually on any scale, it's hard to see what's going on here. So the first thing I can do is actually I can find motifs. So I asked the algorithm to find a motif, and it found this. I'm not sure if it comes from it's here and here, but it doesn't really matter, it's from that. And again, when you see this behavior here, it repeats so well, you kind of believe it means something, but what do I do with it? How do I use it? Well, one thing I could do simply is I could cut the data somewhere, fucking in half, take the average of the first two pieces, put it here, take the average of the second two pieces, put it here, and I'm going to claim this is actually a rule, that this is an antecedent, this is a consequence. If I see this, then I will see this. And there are two things I need to worry about, which is, what do I need to see this? What's the distance between this and the data that I accept as being seen this? And I actually estimate that by being twice the distance between the red and the blue. Another question is, how long after I see this will I see this? And for the moment, I'm going to say instantaneously, but actually I can generalize that. So now my claim is I have a rule, and if you give me more of this data, I think my rule will actually predict that data. And of course, prediction is a very, very cool thing to do. If you can predict certain things, you can make money or save a heart attack, whatever it might be. So does it work? Again, here's the rule. I looked in new data, and in new data, the rule fired. And yes, it correctly predicted what I would see next. It does actually work. So let me now tell you what the data actually is. This is actually the first two choruses of The Raven by Edgar Allan Poe, spoken by an American actor. And it's transformed into NRCC, just one coefficient. And so that happens, the rule corresponds to, the first part corresponds to at my chamber, and the second part corresponds to door. So of course, in the ASCII space, it's very easy to do. Right? In ASCII space, we can find rules. It's very famous and famous thing at my chamber door. But finding it in real value data is kind of interesting and exciting. And it's non-trivial to do this because people don't speak perfectly, as you might imagine. And the question is, how well does it actually generalize? So it generalizes quite well from American male to American male. So it probably will work for many people in this room, if they inside this home. It doesn't generalize quite so well to females. It doesn't generalize quite so well to non-American males. But we're actually working on this, not only for this domain, but for other domains, is how to generalize this. Now, of course, this actually is, in some sense, a contrived and silly example. But finding rules in data more generally, in astronomy, in space telemetry, in medicine, and whatnot, is a very cool and interesting problem to solve. And I'll just give you one hint of this. We look for rules not in human speech, but essentially in bird speech, or in bird song. So for zebra finches, which are obliging to sing all day long, we actually looked for some rules. We found some rules, and then we tested the rule on the bird the next day, essentially. And lo and behold, the rule does still actually kick in. And we also detected it on other finches, but they were raised in the same cohort, and the rule has actually worked again. And so, why is it interesting? Well, for one thing, other finches actually are used in this nature versus nurture debate, right? To kind of figure out what is cultural and what is innate into the bird. And so by finding out which rules fire and don't fire, we can actually address problems. Moreover, we can actually take some finches and we can knock out genes. So certain genes like the FOXP2 are known to actually affect speech and behavior and memory in humans, and the analog genes in other finches probably do the same thing. So by basically knocking out combinations of these genes, looking at the rules that far, we can actually figure out potentially which genes are involved in which part of memory and speech and so forth. Actually, we're doing this right now. We have a grant for this. We're actually not doing it with other things, we're doing it with mice. It turns out actually mice sing just as well, and mice are actually easier to manipulate and knock out genes. But the same basic idea, with the same actually interesting results. So I think actually rule finding is going to be a very hot topic in the next few years for time series data mining. Sorry. Okay, so we've seen so far that if you do something search effectively and efficiently, you can do cool stuff. You can find anomalies, you can cluster non-trivial data sets, you can find repeated patterns and understand repeated behaviors in the marketplace, in an animal's behavior, that might be. You can find rules, and if you can find rules, you can predict what's going to happen next, basically. So all this is cool stuff, and you can do it in something search, assuming you do it effectively and efficiently. And my strong claim actually is that we're probably pretty close to being done here. We're probably as effective and efficient as we ever need to be, or can be. So effective facility search simply means that we can recognize similarity in spite of some possible distortions or invariances in the data. So we saw, for example, for the images of the fish, they might be invariant to color, might be invariant to size, and so forth. For time series, the zebra finch example, what need to be invariant to? Well, we might be invariant to noise. We always have noise, we can't avoid that. Uniform scaling, in that case, the finch might sing a little faster, a little slower, if it's warmer or cold, will be invariant to scaling. And things like offset, amplitude, and so forth. As it happens, these are almost all trivial to take care of. One of them, warping, I'll explain in a moment, is actually hard to take care of computationally, but we can actually do it. So let me show you just two distance measures that are actually very useful, and explain actually that these are probably all we need. The first is classic Euclidean distance. It's trivial, but very, very hard to beat. So it simply says, given two time series, measure distance between the ith point and the ith point, and those distances, these hatched lines here, are basically squared, summed up, square root of them, and that's the Euclidean distance. And of course, I'm showing the two things apart here for visual clarity. Normally, I would push the two sequences together by z-normalizing them so that the red will couple the blue, or vice versa. And for many real-world objects, this is very, very nice to measure. So, for example, it turns out that all howler monkeys, sex species, they're basically the same skull. Right? There's not much difference in them. They have this massive jaw here, which kind of resonation chamber to make a very, very loud sound. But here, basically, the ith point to the ith point corresponds to the tip of the nose to the tip of the nose, or the base of the jaw to the base of the jaw. And those are beautifully aligned. There's only one kind of howler monkey. And then this measure is called dynamic time warping. And here's quite a difference. Instead of mapping I to I, we can actually map the I point to the I plus 1, or the I minus 1, or 2, or 3, or 4. And we can actually map a single point to multiple points. Right? It turns out actually this ability to map multiple things, and to allow this kind of distortion in the time axis is very, very important for many biological and physical phenomena. So for starlight curves, and I'm going to summarize here, for heartbeats, of course, for all kinds of behavior, we actually have to be able to do this one-to-many mapping. So my visual example of this actually is gorillas. So gorillas are highly sexually dimorphic, and the male skull is very different than the female skull, much less different subspecies and tribes of gorilla. And so a movement or increasing the size of the brow ridge, in one example, corresponds to a shift in the x-axis. And this warping, the number 10 warping, allows us to actually take care of this. So this number 10 warping stuff turns out to be very, very useful. It's actually anything biological, you have to have it. And many other kinds of physical phenomena, you really have to have this. So I'll show you two distance measures, Euclidean distance and number 10 warping. And as it happens, the number 10 warping assumes Euclidean distance as a special case. So really, I've only shown you one thing, which is number 10 warping. Now if you look at the literature, you'll find hundreds, maybe a few thousand different distance measures. And my claim actually is they're all worthless. Of course, the original authors would not claim that. They published a paper where they tested their new method against number 10 warping on 2 data sets. They were better, and they said, thus, we are better, use this. And my claim is they're all wrong. So it's a strong claim to make, but let's actually kind of answer the question empirically. Let's do a bake-off. And let's test on every publicly available data set. So to reduce the chance of data bias, of only picking data sets that are good for us, cherry picking, let's test on every public data set in the world. And let's beg every data set we can get our hands on. We have 43 of them. And we actually asked the original authors for their code, for their advice. We ran the algorithms and we actually showed the results and said, can you make it better, and so forth. So it really is, I think, a very, very fair setup for this. So I got lots of results, I can show you all of them, of course. But here's one typical example. Here's a paper that was published, actually 8 or 9 papers published in the same algorithm in different places. And the claim was that this actually T-quest thing is better than number 10 warping. That only the number 10 warping comes close to it, but really not all the way, it is better. But it turns out actually on fair experiments, it's always worse. And sometimes actually basically like the default rate, essentially as good as random. So why did this person and other people make these mistakes? And of course, it's easy to make mistakes in machine learning, right? It's easy to overfit, it's easy to actually consciously, unconsciously bias the algorithms or bias the data sets or bias counter choices to make you look good. It's also easy to cripple a libel. So you can get the number 10 warping and you can implement it in certain ways that are naive to kind of make it very ineffective. Now, of course, I'm not claiming this individual or any other people deliberately did this, but they have done this. And it turns out actually that of these hundreds of papers that have different measures, essentially they're all pretty much worthless. They're slower and less accurate, have more parameters. What's the point? Of course, there might be a data set out there somewhere in the world in which they are better than warping, but I haven't found a data set, and they haven't. So I think effectively, let's forget about it. So my point actually is that if you need to find this measure, warping is probably all you need. And I have very, very strong empirical evidence to show that. So if you believe that warping is all you need, number 10 warping, now the question is it effective? Is it fast? Because again, we have very large data sets potentially. And again, if you read the literature, people will say, no, it's too slow to be useful. So here's some quotes. The number 10 warping incurs a heavy CPU cost. The number 10 warping is limited only to small data sets, and so on and so forth. People pessimistically say the number 10 warping is simply too slow for real streaming large big data type problems. And once again, they're wrong. In fact, they've been wrong for 10 years, but now recently they've become a lot wronger. And I'll show you why. So the number 10 warping basically corresponds to taking the 2 time series and finding a path to this matrix which corresponds to some alignment. And essentially, if you go straight diagonally across here, it's Euclidean distance. If you go off the diagonal, you're kind of stretching time or slowing down time to make one feature map better than another feature. And so any path to this is a warping path, and the path that minimizes the overall distance here is called the number 10 warping. I know I'm glossing over this, but that's all you can know about this. Now clearly to do this for 2 time series is n squared. You can't avoid that. You can build a matrix with size n squared. But as it happens, we almost never want to do one comparison. We have the following situation. We have a long stream of data, maybe a year of customer data, maybe a year of heartbeat, whatever it is. And we have one query that we want to have, maybe our section of DNA or it might be. I'm going to find its best matching anywhere within here. So this actually naively would be n squared lots and lots of times. But about 10 years ago, I showed a nice result that says that in this case here, you can reduce the amortized cost of non-warping from n squared to n in this case. And I modestly call this idea the LBQ. So actually, I happen to be my most famous result, and it's widely used. There's maybe 1,000 references, of which about half of them people actually use this. And so people use this simple idea in motion capture, query by Hammond retrieval, all kinds of problems. It's actually caused an explosion of work done in warping about 3 years ago. But the cool thing actually is, I'm going to make the following claim, which is, I can do better. I actually can now solve the problem in amortized constant time. And I really believe actually it's going to open up a whole new area of data mining. Now, problems that were just simply untenable last year are now finally actually tenable. If we can actually do this not in square time, but in constant time, we can look at really massive, massive problems. Let me just give you some quick examples, and then I'm going to finish up for the day. So we can take a year of heartbeat data, which is about 8.5 billion data points. And by the way, I don't have a year of a single person, but I have hundreds of 24 hours for individual people. I just add them all together. So I can take a year of heartbeat data, and I can search the whole thing for a heartbeat in about 18 minutes. So this is much, much, much faster than real time. Another way I look at this actually is I could actually embed the algorithm into an iPhone or into a small computer on a watch, and I could actually measure in real time on a very, very low-power computer. This actually, by the way, is an off-the-shelf Costco machine. It's not a supercomputer. Another way I can show you this actually is by the size of the data we're actually looking at. So I call this the UCR-ED, it's the included distance version, and the UCR non-time warping, which is the constant time non-time warping version. So about half the papers in the community that I work in, KDD, ICDM, ICML, and so forth, look at data sets which are smaller than a million. Most of them don't get up to a million. We can actually do a million in about an eighth of a second. Only one paper in that community, including Sigma and DLDB, only one paper has ever looked at a billion time series, as happened with my paper 3 or 4 years ago. And we can search a billion objects, time series objects, with non-time warping in about 2 minutes. And again, this is a Costco computer, this is not a supercomputer. And then finally, no one's ever looked at a trillion time series. In fact, if you take all the data sets in all those conferences and sum them all up, it's still less than a trillion objects. And we can actually look at a trillion objects in about 3 hours from Euclidean distance, and in about a day and a half with the non-time warping. So I really do believe this simple result, which will be published in KD this year, is going to actually change time series data mining in a way where we can simply address problems that are much, much, much larger than were tenable only a year ago. Lovely. So my conclusions. If you have streaming of time series data, semantic search is a very simple idea, but algorithms that use that let you solve almost any problem you want to solve. Outlier discovery, anomaly discovery, rule discovery, repeat discovery, classification, clustering, segmentation, summarization, visualization, really all comes down to fast, clever semantic search. My other claim is, with very, very few exceptions, the non-time warping is probably all you need. There's nothing else really out there that's better than that. And my final claim is that, based on unpublished results, that doing the non-time warping on billions or trillions of objects is now actually tenable. We can now do that, otherwise we couldn't do that last year, and certainly couldn't do it 2 years ago. Great. At this point, I'm done. I have any questions. Sir.
Okay, you're searching through a large database for something, and of course, everybody knows one of the hard problems is how do you evaluate the significance, the statistical significance of the search when you stop when you found something interesting. So there are 2 related questions that I have for you. To solve that question, you need to know what you were looking for in the first place. No method can find all possible rules. You must have some set of patterns or rules that you are looking for in the first place. So the first part of the question is what is that, the description of that set, and then how do you, at the end, evaluate the statistical significance of that?
It's actually a great question. I like it. So the question here that we came back to is how do you know the significance of what you find? So if you do outlier discovery, you do rule discovery and so forth, how do you know if it's interesting and significant? So part of the answer to the question is, in some cases I don't. So I must admit, in my lab, my skill set is actually finding these patterns. And evaluating significance is something that I'm not a skill at, I'm not self-sufficient. I can do some stuff with it. So in some cases, actually, the answer is external evaluation. So when I found these patterns, I went to the video and looked at this entomologist. So in some cases, the answer is kind of trivial. We asked someone to do a follow-up test. Visually, you might say here, it's actually close significance kind of visually. But there are some tricks that we can do in some cases. So actually, we're looking at MDL, in the description event, to not only find patterns, but basically score them as how likely they are to happen by chance. And if we know that it's very unlikely to happen by chance, we will give it some significance. That's one possibility. Another possibility is you can kind of learn the threshold. So, let's see here. So this example here, we found an anomaly, and the question is how do you know if it's significant? Well, its distance to the nearest neighbor is, say, 5. In previous data that was undertaken, we did the same kind of a test, and this is the nearest neighbor is always the largest distance, it's always 1.2. So we can simply say that compared to previous shuttle launches, this one appears to have a greater discord. But the general question, so there are some domain-specific tricks you can do, but the general overall question about significance, I fully admit, is still an open problem in almost all cases. And we almost always now at least resort to kind of ad hoc domain kind of tricks. An overall theory of that would be wonderful, and probably not the right to do that, unfortunately. I don't have that skill set, but I would love to work with somebody here who can help me with that. The question? Sir?
How does this apply to multivariate data?
So how does it apply to?
Multivariate data.
Multivariate data. So I've shown you basically one-dimensional data that is easy to see on the screen, but almost all these algorithms could be applied to multivariate data. The only problem with multivariate data is, of course, that with enough variables, it tends to get the problem of correct dimensionality. I'm going to do one example of this. We did some data set for American Sign Language, and the original data set had, I think, 64 dimensions. So every single finger band is recorded, the XY position of patient and so forth. And we got okay results in four-dimensional data, but if you throw away all the 4 dimensions, turns out you actually get much better results. So really, in that case, the clever thing actually is throw away the relevant data, throw away the redundant data. And of course, our tricks to that, like SVD and other things, once again, we often reduce the kind of domain-dependent tricks of asking the expert motion capture, asking the entomologist, which are the good features. That's kind of a more general problem. But once you have to find features, all these algorithms generalize clearly.
About 100, 150 variables.
Again, my previous experience suggests that there are very few problems in the world that need more than 5 or 6 variables. So, of those 150 you have, my guess actually is that either directly 4 or 5 of them, or something in a combination of them down to 4 or 5 will probably be enough. And if you use all 150 of them, you probably will get bad results. So the step you have to do to go from 150 to 4 or 5, I really can help you with, better than I some experiences. But if you do that offline by yourself as experts, and you need those 5 dimensions, then all this stuff works off the shelf.
With physiological data,
yeah,
it is not a good idea to get rid of variables because we don't really know how many affect each other. So we really don't want to eliminate variables. So it really stays to 100, 150.
I think that my colleague David Keogh has been talking about, and he has some data sets where for some diseases actually you need each 3 or 4 dimensions. But for different disease, you don't need actually different dimensions. And really, I have no way of knowing that. And algorithmically, I might be able to discover it, but maybe not. So kind of pushing into the general domain expertise really is helpful there. I think my goal is to build totally black box algorithms. That's always going to be very difficult. It always takes some expert to tweak it a little bit, or at least be in the loop for multiple iterations.
How about other categorical data or point process data? Do you still believe that any more capabilities with this data? And if so, how do you adjust?
But there's a danger that I'll come across in the guy who has a hammer and every problem is a nail. But in many cases, you take categorical data and you can make it into time series data. So I want to show that DNA is actually very quickly changed into this. Things like text can be actually changed into the time series, or the versus text can change into time series. So my first pass is often to take the data and make it the time series as possible, simply because I have fast, efficient, cool algorithms for that. If it really is pretty categorical and you can't immediately change it into a time series, then yes, you have to kind of somehow link these things together. And if a mixture of these things, categorical and binary and time series, it becomes a bit tricky. But in principle, these ideas will work using an extra wrapper rather than to integrate with the categorical data.
How about point process?
I don't know what that means.
You have event paths, like say when earthquake hit.
Again, without thinking about my guess is probably some transformation might actually tweak that into kind of a time series. I mean, even things like graphs, XML, it's a bit unnatural, but you can't put it into time series, and it can really be very fruitful. And often you can hide that from the user. So the user is looking at graphs or trees or XML. Internally, the time series algorithm is working, and give the result back. You can transform back into XML again, essentially. But to make it fast and efficient and effective, is to turn it into a time series. So if you can find the right method, I'd probably help. Sorry.
Curious in the DNA sequence example, have you tried, obviously the encoding from say A is E plus 1, C is E plus 2. That encoding is completely arbitrary.
It's completely arbitrary.
Have you tested whether, if you use an alternate encoding, obviously the shape of the time series is going to be different, but whether the ultimate results are robust against playing with that encoding?
It's a good question. The answer is we have tested that, and it makes no difference what we do. But it is, yeah, it's interesting. It makes no difference. But it is known that for certain animals, not all the 4 basic species different. That's known. And maybe you could try to make this a little bit higher variant than it might be. But at least in principle, kind of rough scale we're working on, it makes no difference what the curve is.
We don't know what's under the hood with your algorithm yet, right? So we'll wait to find out your order constant. But I assume it's parallelizable in the sense that order constant may not be fast enough for some applications.
Something actually, it's pretty parallelizable. So if you have hardware to probe this, the top part of that.
Just your example of Costco PC.
The loud part.
The Costco PC?
Yeah.
So you had a PC share. What were the size of the
Exactly, again, is that.
You said that you had a commodity PC.
Oh, yeah, sorry.
And that you ran on a billion event series. What were the sizes of these event series?
So the time has a length of trillion, the query is length 128. But actually, because of a constant time, essentially, the length of it is almost irrelevant. So if it was twice as long time series, it might be a tiny fraction slower, but not much.
Just imagine, RAM, storing that data.
As actually, the time I showed you actually includes the disk at this time. So it's about, I think, 8 terabytes sitting offline, but it's just on very cheap external hard drives. It's actually for this problem that this time is irrelevant compared to the CPU time. So it's about 8 terabytes of data on the hard drive. Right.
You mentioned noise as an invariant. Do you have a way of incorporating known measurement noise estimates? You have 2 time series, you know this one is noisier than this other one, or this particular subset is 10 times noisier. Do you have a way of incorporating that into the search?
Maybe. So for a certain case, actually, we have a measure called complexity from data set. So that is the bias of something measured for more complex things. Basically, more complex things appear to be further away than you'd expect otherwise, than simple things essentially. And we can actually adjust for that. So these system measures actually do allow kind of domain dependent adjustments. There might be that if you understand the domain very well, what it might be, you might want to say, take the log first and then do this, or whatever it might be, just kind of smooth. And essentially, anything you do, in some sense, I'm probably agnostic to. So you can tweak or pre-process, or even push some of these ideas into the measures directly, and it'll probably make no difference between kind of time and what have you. But again, it kind of requires you to understand the physics of the domain. I don't know where I hand off that.
If you have any idea of the distance Google correlate use?
Distance?
Google correlate. It's the inverse function of Google Trends.
Oh, yes.
And you have any idea of the kind of distance they use in this system?
I haven't worked with the Google Trends thing. I have looked at, before Google Trends came out, Microsoft gave me some of the data to listen to this. And actually, I have looked at this a little bit. It's actually interesting data to play with, but I don't really have any great experience or feedback with that.
Yes, for ETM, it seems like we ignore the sorry, for ETM, it seems like we ignore the lead lag relationship between the two series. But sometimes it's kind of lead lag information could be interesting.
Lag?
Yeah, lead or lag.
Oh, sure.
Yeah. So,
sorry. But the question was involving the lag. So for the rules example, in particular, in the first example I showed you for Raven, I said there's no lag, that immediately after the antecedent fire, the consequences happen. But actually, we generalized this actually to handle some kind of variability. To give you a nice example of this, we had this other in iPhones, and we found this data set where we actually got this beautiful kind of a concave lip, and then a flat piece, and then a reverse concave lip, and a flat piece. And what it corresponds to is an elevator. You went to the elevator, and there's no acceleration initially in this direction, of course. The elevator starts up, and you get this kind of acceleration. The elevator stops, you get this little blip again. Now, the linear lag between those depends on how many floors you have. So we learned the rule in our building, which has four floors, and we had a maximum lag. But of course, when I go to New York and have these new skyscrapers, the lag and lead can be much, much larger. So we can generalize a little bit of that from that. And of course, the domain expert can come in and manually edit that, saying in Hong Kong we need a longer leading lag. But so that will be the main dependent, of course, too. Of course, inches and how do you put it way different.
How do you code in shape as a time series?
Yeah.
Something that's not star shaped. How do you code that?
I'll show you one way to take a shape and make it time series. There's at least 20 different ways of doing that, and some work better for kind of convex or concave shapes, some work better for spiky versus smooth shapes. The answer to that, I don't really care. Any of those ways that you focus your data set, do it, and give me a time series, and I will do search for you. But there are many mappings. What I showed you actually is nice because it's lossless. It's actually one point mapping, but no information is lost. But to some extent, I don't care how you take it.
What about because that's a void?
Sure, I mean, again, there are at least 20 ways of doing this, and some actually do work with donuts, like whole time. Some don't work for donut-shaped things. Just pick one that's appropriate for your domain, and whatever it is, give me a time series, and this all works for you.
So, related question: if you had an image and it is a grid of pixels, and each one has a value, can you encode that as a time series as well?
So the question is, you have a grid, like a box solid or brain scan, and you have values of each part of the grid, and you have to make it time series. You actually have done this like a Hilbert space-time card, where you actually fill the space, and you take the single path and stretch it out and measure that curve, and apparently there's a calculation on that. I haven't done it personally, but I just want to check to actually have done that. And again, people I know have done that and used some of these algorithms. So there are many ways to take the data and map it to time series, and these are kind of domain dependent. Once you do it in a meaningful way, I can probably help you a little bit. But how you do that will depend on the properties of your database.
So you mentioned about reflecting images before you do a mapping.
Yes.
What about things like rotating arbitrarily? When it's thinking of the galaxy.
It's actually a great question, but it's an example of domain-dependent invariances. So the question is basically what kind of invariances you want. In this example, almost certainly left or right has no meaning. The question is, will you allow rotation invariance? First of all, if you do want to allow rotation invariance, I can help you with time series space. Because rotation invariance becomes phase invariance of time series space, which you can easily deal with. When you want to not depend, right? So if you imagine letters, I don't rotate a D. If I rotate a D enough to become a P, right? So I can't do rotation there. I might do limit rotation. I might say a D can rotate 10 degrees, hand by Alex, with no more than that. But the answer to the question is, there's always the kind of domain-dependent information you have to plug in to constrain the warping, to constrain the phase invariance, and whatever it is. And usually you have to either learn those and not data, or have an extra plug. But the algorithm actually can handle essentially any invariances, whether it's offset, scale, rotation, phase, scaling. We can handle all of those. Just tell us which ones to handle, or give us that we can learn to handle.
How do you deal with highly regular sample patterns and gaps?
So the question is, how do you deal with irregular sample data sets? So here we have every single point. So we have every single point here. What happens with missing points? The answer, I have actually a magic solution to that. If we have a few missing points, it will smoothly populate and we'll walk away. But if you have significant amount of missing data, entire days of missing that your space launched because of bad weather it is, the answer I don't actually know. And again, maybe some domain dependent trick would handle that. There's some problems like for electrical power demand. We basically have a problem occasionally, and we go to last year's data, take last year's data, and put it into place this year's data. And for some problems that works fine. It's some problems that can cause a huge problem, like because maybe last year the World Cup was on that day, this year the World Cup was not on that day, and we had this recovery biased result. So it's a generally tough problem I have to particularly very hard to complete.
Are you able to point to sample code and a data set for this approach?
Oh, sure. It's actually that I religiously believe in giving away all data and giving away all code. So if you go to my website, find my email address, or offline, any of the code is that you want, throw it over.
Thanks so much.
Okay, we'll have a couple more questions.
So as predicted, Google did terribly in picking up your accent. If you look on the tag, it says New York and things like that. So have you, you've obviously talked about doing some sort of speech recognition and sort of essentially mapping parts of speech. And you showed us the poll example. Have you tried this with sort of a speech bank and done this in a generic way where you actually tried to do better than what we have here?
So actually, I have not actually. I only use the speech version because actually we all know the right answer and it's kind of intuitive. But I have no particular skills in speech. Speech normally, of course, is a very high dimension, maybe 44,000 hertz signal. And the MLC thing I do makes it into a low dimensional, relatively smooth changing thing where I can find rules in it. It's a good transformation. But in terms of actual speech stuff, I'm not an expert in that, and I'm not going to compete with them. I'm only using it as an example of what I can do.
But in terms of your search, where you're not actually trying to find rules, but you're just trying to find matches. This is a perfect example.
Oh, yes, actually.
You had a big bank of people speaking. You had those well labeled, and for new input speech, you can just search.
No, this is actually so. The Dynamic Warping actually is very competitive with everything else in speech, in terms of market models that it might be. The Dynamic Warping tends to perform almost as good as anything else out there for speech. It's a very simple algorithm. People often don't use it because they say it's too slow. But again, I hope that will change people's minds. Actually, it is very, very fast. So we can search speech much, much faster in real time, even on a low-power device now.
Just to argue with what you were said about speech, what you had said where you were able to do a male American accent, male American accent, but weren't able to go to female or foreign accent. A lot of the challenges of looking at speech involve huge variety of speakers, people like you and I that are harder to understand for most people in this room. A lot of channel effects, and we try to be very channel effects. And a lot of what makes actually searching speech and doing effective speech text work hard in a lot of venues are exactly the sorts of things we were talking about that tends to help within that. So I think you're overstating there.
So now it is true actually that I think maybe I could do better for speech if I deliberately, I took the time to understand it better. That people have this variability to get excited and talk faster, and get calm and talk slower. I can actually encode that for you from a statement, and I can encode some other things that actually might help to be more invariant accent, more invariant and so forth. Again, it probably takes some of the main work to map that and to take care of that into the MLC space. If the data in that space is reasonable, it probably actually help you a lot. Actually, again, I want to point out that I'm not an expert in speech, but people do use something more in speech, and it is quite successful, it's quite competitive. But if you understand speech better and actually do these transformations and corrects with better I can come to this.
I'd like to ask a similar question actually, since you mentioned these and these earlier. Has it been tried on optical character recognizers?
We have actually, there are transformations of single characters and even entire words into time series space. So people actually have done this for historical manuscripts. So some of them look at George Washington's 1 million word writings. And it's joint handwriting. They take the top profile and the bottom profile of the joint word, and it becomes 2 time series. And you search in that space, and it actually is competitive with all the other approaches. So many approaches can be kind of twisted into a time series type of problem. And usually when that happens, if the map is anyway reasonable, time series is both effective, there's a natural variability of human writing, and it's quite efficient now, as you can see.
Actually, I was more interested in something that is printed but not English, because for many Asian languages there are no good optical character recognizers, and if given printed text, it's going to be easier to see given the application.
I think that's possible. We actually have tried for some things like Malaysian and Thai, which is, it's hard to find good off-the-shelf kind of photos for obscure languages, if you believe that. And actually, we actually have some very good results. It's kind of a special domain, and actually, knowing something about that domain, like ascendants and descendants, no kind of thing can help. I don't know that, literally. But just as a quick test, we tried this thing, actually, it works quite well.
Okay.
Okay, I'm going to finish up the question of my own, a more abstract one. You've clearly worked in a number of domains, and in answering these questions, a number of domain-specific questions, and you've indicated a couple of times the difficulty of tackling problems in different domains with a single tool, and there's challenges to each domain. I wanted to ask you to reflect a bit more on multidisciplinary and domain knowledge. I think it's of interest to everyone here to understand a bit more about how to generalize ideas between domains.
Okay. So this structure, I do work in lots of domains, that's interesting stuff. What I work actually is NSF likes that, and some communities like it. Now, I've actually published papers with anthropologists, neonatologists, entomologists, herpetologists, astronomers, cardiologists. There's a few other bodies in there. So it's actually, it's like fun, interesting, and yeah, fun things to like that. I could actually build sort of tools that are kind of abstract. That is a layer where you have to take your data, you have to clean it, you process it, and normalize it to make it kind of a time series thing. But once you've done that, you can plug it into various tools, and you can find the anomalies, the outliers, the big patterns, and so forth. So it is this abstraction layer where we can actually have a domain expert typically tell us that this doesn't matter, but this does matter, and this matters a little bit, what it might be, and that transformation. But it shouldn't be a black box beyond that point, I think, after that. And what about domain expert is, someone really know what they want, but really can't express it. You have to really work very carefully with them, kind of tease out of them what it actually is. Often say intuitive knowledge, and they can't do their mapping as easy as they might like to do. But it makes that very fun, make that.
Fantastic. Okay, let's thank Eamonn again for a wonderful talk. Can I invite Damien to come up?
And then finally, why is speed so important? Why do we care? Well, the obvious reason is, of course, first of all, that the size of the data set might be quite large. We might have 1 million or 1 billion or more objects in this, and measuring this function at every one could be quite slow. But actually, more importantly for what I'm going to talk about today is that very cool algorithms actually call this function as a subroutine many times, maybe 1 million or 1 billion times. So no matter how fast one iteration of this is, doing it 1 billion times could be slow, it needs to be fast. Okay, one last little point here, which is useful a little later, is if I want to actually, I could search for those fish in the kind of time series space. I can actually take a shape, I can find the center of mass, I can unwind it into a one-dimensional sequence, and I can consider a one-dimensional sequence. It's actually the lossy transform. And actually, I'm showing this for two reasons. One, which is we'll pop into a few slides later on. And secondly, it shows an important point, which actually is for many of these problems, the interesting part actually is changing the data from one data source to another. So I'll show you an example of this later on with DNA to time series. But you can change data from one form to another form all the time. And as it happens, it's a useful trick because often problems are easy to solve in one format. Lovely. Well, finally, ready to look at streaming data. We can talk about streaming time series. So I'm going to spend the next half an hour talking about the utility of semantic search. Again, because my claim is, if you can do this well, almost all problems are very trivial to solve. So here's a real time series. And semantic search simply means that I could grab a template, let's say this section here, and I could ask, where is its nearest neighbor, its most similar object, anywhere else in this time series? And my guess actually is this would match pretty well over here, for example. Here it is here. And this function is a black box. And in the black box, you put in two objects, two DNA strings, two fingerprints, in this case, two fish, and it pops out a number. The number itself has no meaning, but the relative numbers do. So maybe the similar fish actually is 2.7 units, but a different random fish might be a much larger set of units here. And the question actually is, for any kind of data you have, time series in this case I'm most interested in, is what's the right black box? What property should it have? And these are the invariances. So for example, I want my black box probably in this case to be invariant to color. And why is that? Well, the early documents were scanned by Google. They were scanned in black and white. They were being cheap. So actually, I want the distance to be invariant to whether it's colorful or black and white. And likewise, the documents are scanned, actually they're not scanned, they're photographed from the distance, and the camera can move in and out, it can zoom. And so the size of the fish is actually only the apparent size. There's no information. I want to be invariant to this. And for many contexts, of course, the direction the fish is facing, left to right, right to left, makes no difference. I want to be invariant to this. So for any similarity problem you have, The question is simply, what do I need to be invariant to? And once you're invariant to those, you're in business. I should point out, of course, this is all context dependent. This is true for historical manuscripts, but in the real world, say underwater with a camera, color will make a big difference. And in the real world, a big fish might be a different species to a smaller version of it. And even this left to right asymmetry actually may not exist in the real world. There are some fish which are asymmetric, flounder in place, and they're asymmetric to the left and to the right, and this actually would make a big difference. So understanding the invariances are very important, and we'll get to those in time series shortly. So with that one core subroutine, let's solve some problems. The first thing I want to do actually was hinted at in the introduction, is find an outliers, anomaly, novelty, and so forth. How do we do this? And there are hundreds, maybe thousands of papers trying to do this, but here's a nice way to do it in semantic search. Let's imagine take a subsequence here, and we ask, what is its nearest neighbor? So this guy here, it's probably nearest neighbor is probably this guy here or this guy here. And actually, for every single subsequence here, I can ask the question, what is the nearest neighbor? And the one that has the largest distance to its nearest neighbor, I'm going to call it a time series discord. As it happens, this one section here in red has a very large distance to its nearest neighbor anywhere else, and hence it's called the discord. And I'm going to say I think it's an anomaly. And of course, as you can guess in this annotation here, it actually is truly an anomaly. It needs to be detected and flagged and whatnot. So this is the way I introduced about 7 years ago to find anomalies in time series. And reviewers initially didn't like it. They said it's just too simple. But later on, empirical evidence showed actually it seemed to work very, 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 very well. And people said, well, it works in spite of being so simple. But actually, that's not true, of course, right? It works very well because it's simple. Because you don't have 15 pounds to tweak, and you can't impose your ideas upon the data set, and it tells you what's anomalous. You don't tell it yet in some sense. So fairly recently, within Kumar did a kind of a bake-off on 19 data sets with 9 different techniques, including this one. And as trivial, as simple as it is, it works beautifully. It wins basically every single time. So my point is, again, that the simple idea of semantic search lets you solve a problem that people find quite complex, finding outliers. Let's look at another example of when we do semantic search. Let's do clustering. So the first thing is, here's a tree. And I'm going to begin by arguing the following. And I use the word argue advisedly, because I'm going to make claims here which actually contradict other people's research and papers, but I'm going to convince you that I'm right and they're wrong. And so my first claim actually is that similarity search is the fundamental operation for almost all stream and time search problems. If you can do similarity search very well, everything else turns out, I think, is easy. Classification, clustering, anomaly detection, and so on and so forth. That's my first claim. And I'll explain what similarity search is in some detail first. My second claim is also kind of controversial, which is that the similarity search problem actually is now essentially solved. We are effective and as efficient as it basically ever need to be, or ever can be in some sense. And now we should actually spend time looking at these higher level problems and not the fundamental search problem. Let me jump right into it with a 5-minute tutorial about what similarity search actually is, and then we'll move on. So similarity search requires us to understand what do you mean by similar. And that really comes down to what are the required invariances for your problem. I'll explain in a moment. And why is it so important to be fast? You probably already guessed why you need to be fast, of course, but I'll do that also. So here's a quick tutorial. It looks contrived, but it's a real problem I'm working on. We have these large archives of historical manuscripts going back 800 years. And let's say we have a query. I find this interesting fish here, and I want to know, are there similar fish in 17th century Portuguese documents, example. So I have my database, I want to search, here it is here. And similarity search simply says, take the query, compare it to every single thing in my database, find the nearest fish, in this case probably that guy there, I'm guessing, and return it as the nearest neighbor. And that's all similarity search is. Now I said similar, and what do I mean by similar? Well, I'm going to have a distance function.
All right, welcome to the first session of the meeting. It's on time series clustering and classification. So I'll introduce the first speaker now, keynote speaker for this session. Professor Eamonn Keogh is Professor of Computer Science and Engineering at UC Riverside. He completed his doctoral work in 2001 at UC Irvine and has won numerous career awards in intervening time and a number of NSF grants, one of which has funded a series of tutorials on topics of machine learning classification, which are available, or information about which is available on his website. Well worth looking at. He's an expert in
solving similarity and indexing issues in time series data. And he will talk today, welcome, on the topic of scaling time series data mining, scaling upward, I presume, to trillion data series. Okay. So, first of all, let me thank the organizers for inviting me here. It's a pleasure to be in their company. If Google can handle my accent, I'd be really, really impressed. I'll do my best to speak slowly. So let me jump right into it. And here's the outline of the talk.